Okay, good morning. What I would like to do is to work on combustion analysis here, which is section 3.5. And but before I get started, Sophia, do you have any questions, any particular problems you want to look at?
Sorry, just hang on. I was just grabbing some coffee. Do I have any particular problems that I want to look at?
Yeah.
I was actually doing something for another class basically all day yesterday
and
haven't had a chance to go over it. I'm sorry.
So anytime, like when we start, we always have some time to do problems that people are working on and have difficulties with. So no pressure, you don't have to have one, but if you do, then we'll do that. Okay.
Cool, thank you.
All right. So let's take a look at combustion analysis then. And there's a few different types of problems that we do in combustion analysis. So I'm going to go ahead and put up one of them. Oops, there it is. I didn't see it there for a second. And okay, no, that's good. Okay, so here's one type. This is actually the first type of problem. Elemental analysis of binary compounds. And it says here that measurements show that an unknown compound X has the following composition. There are two elements in it. The first one is iron and the second one is oxygen. And the mass percents are given at 69.9 and 30.0 percentages. Okay, notice those two numbers come pretty close to adding up to 100. You get about 99.9, and you know, if it's pretty close to 100, that means those are probably the only elements that are in the compound. If it came out to, let's say, 95% and we were off by 5%, that would mean there's probably a third element in it, right? And we would have maybe, you know, people would try to figure that out. But in this problem, it says to find the empirical formula of X. And the empirical formula, that's one of the experiments we do in the laboratory, is we find the empirical formula of a copper oxide compound. And so this is kind of a similar type of issue. It's a similar type of problem, actually, that we do in the laboratory. So let's take a look at it.
So iron is 55.85 grams per mole. And so we're gonna divide, what was the problem again? How many? 69.9? So we're gonna divide 69.
Yeah, exactly. So iron,
right?
Now I'm gonna put a separate column in here, Fe for iron, right? Which is 69.9%. And then the second one is oxygen. The symbol for oxygen is O, which is 16.00. I'm sorry, I'm getting ahead of myself. 30%, 30.0. Okay. And what I'm going to do is I'm going to put over here the molar masses of each of those elements. So for iron, it's 55.85. Remember, molar mass is grams per mole. And then oxygen is 16.00. So that's in grams per mole. Okay. Now, essentially, the idea is this. There's some compound that has iron in it and it has oxygen in it. So those are the two elements that make up this substance. And what we're trying to do is we're trying to figure out what the ratio is of these two. So how many irons to how many oxygens? And here are some possibilities. It could be 1 to 1. There could be 1 iron for every oxygen. Maybe there's 2 irons for every oxygen. Maybe there's 1 iron for every 2 oxygens, or 1 to 3, or 3 to 1. The empirical formula is the lowest ratio of whole numbers for each element. So for example, if I had Fe2O4, we could reduce those two numbers. The ratio is 2 to 4. Well, that ratio 2 to 4 is the same as 1 to 2, right? So the empirical formula never shows, you know, higher numbers like 2, 4, 3, 6, multiples of each other. It always shows it in the lowest possible ratio. So for
So
this
if you
one,
want to however many of the other one.
yeah. So that would be like FeO2, 1 iron to 2 oxygens would be the empirical. Now, this is called the empirical formula. And there are cases where this, you know, we might be interested in looking at that, but for empirical formulas, we always use the smallest whole number ratio, okay? So the nice thing about these problems is that when you go through them, it works itself out pretty well. It's pretty simple, okay? So let me show you how we do this. This is the most standard method for this type of problem. What we're told is these percentages, these are by mass, percent by mass. So what this is saying is that essentially, if you had 69.9 grams of iron in this compound, so you weighed it out and you found that there was 69.9 grams of oxygen. Of iron. This compound would absolutely have to have 30.0 grams of oxygen. Those mass ratios are fixed for particular compounds. So for example, if I have FeO, let's say that's the formula. If I have 55.85 grams of this, I have to have 16 grams of that. Why? Because it's 1 atom of iron for every atom of oxygen, and 1 mole of iron weighs 55.85. So if I have 1 mole of iron and that weighs 55.85, I also have to have 1 mole of oxygen and that has to weigh 16. So what that means is every compound, whether it be FeO or Fe2O or Fe2O3 or Fe3O4, whatever that compound happens to be, each compound is going to have a specific percentage breakdown, a unique percentage breakdown. So if I know it's 69.9 and 30.0 percentages, I know it's got to be one of these, but it can't be 2 of them. It can't be 3 of them. It can only be one of them. And that's what's very useful about these types of problems, is that it allows us to identify a compound. We can figure out which one of these it is just by looking at these numbers here. And what I'll do is I'll show you how to do that calculation. Okay, so let's erase this mess over here. Okay. The ratio of 69.9 to 30 can be done in terms of mass as well. So here's how you could do it. So I'll write this as mass ratio, and this is going to be in grams. What you can do is you can say that this is 69.9 grams, and this is 30.0 grams. Because this is a mass ratio in percentages, so the mass ratio in percentages should match up with the mass ratio in grams. So that's kind of cool. Now what we can do is we can go back to section 3.4, which we talked about. Actually, we talked about it last week, last Thursday. We can always do gram to mole conversions using the molar mass. Or we can do mole to gram conversions using the molar mass. Now, if we're going from grams to moles, what you do is you divide by the molar mass. And if you're going from moles to grams, you multiply by the molar mass. So since these are in grams, we can convert them to moles. So what we'll do here is we'll convert these grams of iron and oxygen to moles. of iron and oxygen, okay? And if you're going from grams to moles, you divide by the molar mass. So 69.9 grams of iron. Let's divide it. So I'm going to use dimensional analysis. 1 mole of iron is 55.85 grams of iron, right? Of course, that's from the periodic table. Let me just make sure I got a little calculator here. Oh, and bring my calculator. I'm sorry, hold on 1 second. Let me go grab it. Okay, so that comes out to 1.2516 moles of iron. And then we'll do the same thing for oxygen. 30 grams of oxygen. 1 mole of oxygen is 16.00 grams. Again, that's from the periodic table. And you get 1.875 moles of oxygen. Okay, now the reason that we're going from, the reason that we're looking at converting them to moles is the following. When you look at a chemical formula, so let's say the chemical formula is FeO, we can interpret that as meaning 1 mole of iron and 1 mole of oxygen. Because remember, a mole is just a number. So if I have some number of irons, I have some number of oxygens. So if I had Fe2O, we could interpret this as 2 moles of iron and 1 mole of oxygen. So by getting these into moles, we're going to be able to take those numbers and convert them into a formula using subscripts, okay? Now, for this particular problem, let's take a look at what happens. This is not a whole number. We want whole numbers for chemical formulas. We don't want to have Fe 1.25, O 1.875, even though those do show the ratios. We want to have whole numbers. So it's just a matter of figuring out how to get whole numbers out of decimal numbers. What you do is you divide by this, divide each value by the smallest number. So if we had 3 elements and one of them was the smallest of the 3, we divide all 3 by the smallest. Here we only have 2 elements. So here's what you do. So for the iron, iron is the smallest. It's 1.25. That's smaller than 1.87. So we divide iron by itself. Well, that's going to give you 1, right? So one of the things, a feature of this is that you always, one of them is always going to be 1 because you're dividing by the smallest and there has to be a smallest. So you'll always get one of them as 1. But now let's divide the oxygen by the smallest. So oxygen over iron. So dividing by the smallest. So that would be 1.875 over 1.2516. Now, sometimes what happens is it's really nice. This will come out to a whole number. It'll come out to like 1.99 or 2.01, 3.01. Sometimes you get something that's not even close to a whole number. So let's take a look at this one. 1.875 over 1.2516. This one, you do not get anything even near a whole number. This is way off a whole number, okay? So now you have to kind of reason through what this means. If you look at this number, it's very close to 1.5, really close. See, 498 is almost 1.5. Now, what does 1.5 mean in mixed fractions? As a mixed fraction, 1.5 means 1.5. So we don't have a whole number, but we've got kind of a number that we're familiar with. We have 1.5. So here's what we do. We essentially at this stage have iron is 1 and oxygen is 1.5. So what we do is we multiply by 2. Multiply each of them by 2. So here's what happens when you multiply each by 2. 1 times 2 is 2, so you still have a whole number. 1.5 times 2, that gives you 3. You now have a whole number. So now they're both whole numbers. So if you get a number that's about 1.5 or 2.5 or 3.5 or 4.5, just multiply by 2, both of them by 2, and you will now have whole numbers. So now we have Fe equals 2, O equals 3, and we can write that as an empirical formula. Notice those numbers, 2 and 3, cannot be reduced to smaller whole numbers. If we divide them by 2, that doesn't work because 3 divided by 2 is 1.5. And if we divide by 3, that doesn't work because 2 divided by 3 is 0.67. So now we have what's called the empirical formula. And this is a powerful method because what it says is, if you have mass percent values in a compound, you can figure out what the chemical formula of that particular compound is. It's a specific type of chemical formula. It's called the empirical formula. And there are some limits to what that means, but essentially you now know what the relationship between iron and oxygen is in this compound. It would mean that if you actually analyzed it, you would find that for every 2 irons, there would be 3 oxygens attached to it. And we got that from these mass percentages. Notice the only numbers you needed were the percentages and the molar masses from the periodic table. No other data was required in order to get that. Okay. That's called empirical formula. Let's take a look at one more. Okay, here's one with chlorine and oxygen. Let me pop this one up so you can see it. There we go. Again, elemental and binary. Binary means 2, right? So like in digital, in computers, binary 0, 1, 2 possible numbers. There's a whole mathematics of binary number systems as opposed to decimal number systems. Or maybe you've heard of a binary star system, right? A binary star system is where you have 2 stars in orbit around each other, right? So I think the nearest star system to the Earth is the Proxima Centauri system. I think it's actually a trinary. I think it actually has 3 stars, but many systems are binary. Okay, so binary means 2 elements in this case. So we're just doing 2 elements, not 3 or 4. But you could do this problem with as many elements as the compound has. So here we have chlorine, Cl, and oxygen, O, and find the empirical formula of compound X. Very similar type of problem, right? Notice here there's more oxygen in terms of mass percentage than there is chlorine, whereas in the previous problem there was more iron than oxygen. So it just depends. It really depends on how heavy the element is. Iron is 55.85 grams per mole. Chlorine is about 35.45, so it weighs less than iron. So it's probably going to have a lower mass percent. Okay, let me just move this over a little bit so you can see the numbers. Okay, so chlorine, I'll write the symbol down, and it's 38.7%. So there's your mass percent. And then let's do the molar mass. 35.45 grams per mole, right? Those are the units. 35.45 or 35.453, depending on how many sig figs you have. Try to keep at least, when you do these calculations, try to keep at least 2 digits past the decimal point. I wouldn't round it to, I've seen people round it to 35 or 35.5. Try not to do that. Keep at least 2 digits there. Oxygen is higher now, 61.2. And let's see, 61.2, and it's 16.00. Okay. So in terms of what I know there is a ClO2. I know that exists. I'm pretty aware. I think there's a Cl2O that exists. There's also some Cl2O7 that exists, but I'm not sure about others. But those are at least 3 that I've heard of. So let's take a look here. Again, the idea is if you're given the percentages, you can just write those as grams. And then now you can do, you can convert to moles. So if we have 38.7 grams of chlorine, we can convert that to moles. Okay, it's going to be a little more than 1, right? Take a look at those numbers. If you look at them, if you're dividing 38 by 35, you're going to get something a little more than 1. So if you do this and you get something less than 1 or 2 or 3, you can immediately tell that you probably punched the calculator wrong. I do it all the time. I make mistakes on the calculator all the time. I don't trust the calculator, to be honest with you. So sometimes I'll just check myself just to make sure. Okay, and then do the same thing for oxygen. So for oxygen, it's 61.2 grams, and it's 1 mole of O per 16 grams. .825 moles of oxygen. Okay, so now take a look at that ratio. This is actually probably, it's probably going to work out to being pretty much whole numbers. I think we can figure that out. So now you divide by the smallest, by the smaller. So chlorine is the smaller one, right? 1.09 is smaller than 3.8. So that would be 1. That just gives you 1 automatically, right? That one's easy. Now you do the, you divide by the smaller. So oxygen over chlorine, 3.825 divided by 1.0917. To be honest with you, that looks like 4 to me. It looks really close to 4. No, actually it isn't. That's not 4 because 1.09. Yeah, I'm not sure what that is. Let's see.
Oh, I got 3.5.
I'm sorry, what?
I got something closer to 3.5, and then it would
Okay. When you did the division?
Yeah.
Yeah, me too.
Yeah.
3.50, right? That's 3.5, right? That's 3.5. That's really close to 3.5.
Right.
So now, same thing as last time. You've got 1 and 3.5. Just multiply both by 2. And that's 7. So now you've got Cl2 and then O7. And that's actually that one right there. Okay. Cl2O7 is probably something I've never actually seen a diagram of it, but it probably is this. Probably looks like that. Wow, that's an interesting molecule, actually. We'll get into Lewis structures later in the course where we'll actually be able to draw out all the electrons and see what the structure looks like, but probably looks something like that. But in any case, this is the empirical formula here. Okay.
Professor, I have a question.
Yeah, go ahead.
Are you able to find the molecular formula just based off of the empirical formula?
You need one more piece of information. So to go from the empirical formula to go to the molecular formula, you need the molar mass of the compound. You need that piece of information. Okay? So in this particular problem, they didn't tell us, but if they told us, so let's say they did this, 35.45 times 2 plus 7 times 16. Suppose they had said, hey, here's one more additional information. The molar mass of compound X is 183 grams per mole. If that was given, you would now be able to calculate the molecular formula. Okay. We'll take a look at one of those in a little bit, okay? That's the next, it's actually essentially the next type of problem. Okay. So let's see. Okay, so let's actually do that. So what I'm going to do is I'll bring this up so you can see this one. It looks very similar. It's a very similar type of problem, but it's a slight difference here. If you take a look, it says that compound X has a molar mass of 266.64 grams per mole. Now, when it says G dot mole minus 1, that means grams divided by moles. And the following composition. Again, the same thing. There's two elements. There's aluminum, there's chlorine, the mass percents are given. But now notice it says find the molecular formula of X, not the empirical formula. So what we do in this case is we do it just like we did before. We find the empirical formula. But now this additional piece of information where they tell us the molar mass of the compound, that piece of information right there can be used with the empirical formula to find the molecular formula. Okay, so we'll do this problem, but let me show you what the difference is between those two ideas. So the empirical formula it tends to have ratios that are very small. 1 to 2, for example. 1 to 3, for example. 2 to 1, for example. But the molecular formula is not constrained by that. It can be very large ratios. So for example, see here we have 8 to 16 or 9 to 18. So the molecular formula can have these very large ratios. And notice these are not the smallest whole number ratios. So the relationship is essentially this. This empirical formula is just a ratio. Carbon to hydrogen, for example. The molecular formula is the actual number of atoms. That's the difference. The molecular formula is the actual number of atoms. So for that reason, this is actually more useful. If you have the molecular formula, that can be more useful information than the empirical formula. So here's an example. There's this compound called benzene. And I'm going to draw out the structure of it here. Benzene is a very interesting molecule to chemists because it has interesting physical and electronic properties that we'll get to a little bit later in the course. Okay, so there's benzene. And that's actually what we would call the structural formula. This is called a structural formula. Okay. Now what you can do is you can convert this to a molecular formula very easy. You just count up the number of atoms of each element. It's got 6 carbons, right? So we would write this as C6. And then we could count up the number of hydrogens. Write that as H6. And this would be your molecular formula. Right? Right there, C6H6. So it's just the actual number of atoms in the molecule. But you could figure out what the empirical formula is too from the molecular formula, what you would do is you'd say, okay, we have 6 and 6. What can we divide 6 by to make it a smaller whole number? Well, you could divide it by 2. So that would give you C3H3. You divide both of them by the same number. But you could also divide by 3. So if you divide it by 3, that would give you C2H2. However, you could also divide them both by 6. 6 divided by 6 is 1. So if you divide each of them by 6, you get CH, right? 1 carbon, 1 hydrogen. That's the smallest whole number ratio. And that would be the empirical formula, okay? So typically the way we teach this in this type of course is we teach you how to do the empirical formula first from the mass percent data. And then we give you a problem where you go from the empirical formula to the molecular formula. And then later in the course, you figure out what the structural formula is from the molecular formula, right? So that's sort of the progression of what we do. So for right now, we're at this stage where we figure out the empirical formula, and then from that, we figure out what the molecular formula is, okay? So let's try it with this problem on Alex. It's using aluminum and oxygen. Okay, so first, let's figure out, let's write down what the molar mass is. That's given, 266.64 grams per mole. Your textbook by Birds usually, they usually just say it's like 267, they'll round it off, and that's perfectly fine. But Alex, they give you a bunch of sig figs, which you don't really need. Essentially what I would say is this is, 267. Okay. Then they give you the mass percent. So aluminum is the first element, and it's 20.24%. And oxygen is the next element, and it's 79.76%. Okay, so those are 2 elements. Again, notice those add up pretty close to 100. In fact, in this case, they add up exactly to 200. Exactly up to 100%. So I'm going to write down the molar masses here. So oxygen is 16 grams per mole. And actually, let me look up aluminum. I forget what aluminum is, like 26, I think. So molar mass, aluminum, 26.98. So it's actually a little closer to 27, right? Okay, there we go. So again, what we said was that if you've got percentages, you can just write those percentages as grams, because that is a mass ratio they're giving you. So it's 20.24 grams of aluminum, and it's 79.76 grams of oxygen. This one's it should work out to be 2 to 3, we'll see. However, let's go ahead and figure it out here. So we've got 20.24 grams of aluminum. The molar mass of aluminum is 26.98 grams. Right? Divide by molar mass to get moles, and multiply by molar mass to get grams. That's the general pattern. 20.24 over 26.98, and you get 0.7502 moles of aluminum. And then you got 79.76 grams of oxygen. 1 mole of O is 16 grams. Okay. So 79.76 over 16, 4.985. Wow, that's a big ratio there, right? That's interesting. So a little bit less than 1, and then that one's going to be quite a bit more than 1. Okay, so divide by the smaller. The smaller is the aluminum, right? This one's smaller. Okay, so for aluminum, it's going to be 1, right? 0.7502 divided by 0.7502 is 1. That's clear. Now let's do the oxygen divided by aluminum. Okay, so 4.985 over 0.7502 Well, that's going to be, I don't know, like 6 or something like that. Let's see. 4.985 over 0.7502. 6.6. Okay, this is cool. 6.64. Okay, now this is different, right? We get a different issue here. That is not really very close to a half. 0.64. However, let's think about fractions. If you have 0.5, that's a half. If you have 0.33, that's a third. If you have 0.666, that's 2/3. If you have 0.25, that's a fourth. And if you have 0.75, that's 3/4. Okay, sorry, it's hard to see that. Okay, so if you look at this one, you got 0.64, that's pretty close to 2/3. Okay, so that's right there. So the way you deal with this one is you multiply them by 3. Okay, so that gives you 3 there. And then this would be 6 2/3. Well, let's figure it out. Times 3. It's 20. Boy, that seems high. Right? Boy, that's crazy. Oh, I see. I made a mistake. Okay, good. I was going to say that just seemed kind of crazy. Here's what happened. I wrote down the wrong element. Sorry. So this was actually supposed to be chlorine. That makes much more sense. That changes that number. Okay, so everything I said here is kind of true, but I did the wrong calculation. So I'm going to go back. It's aluminum and chlorine, not aluminum and oxygen. So let's get rid of the data on oxygen.
So, Professor,
Mm-hmm.
I'm actually kind of glad you made that error, because I'm wondering if we're going to get a problem where we're going to have to deal with a fraction that's a little bit more complex than the, 0.5.
Yeah, it could happen. It could. I haven't seen any here today, but it could happen. You could get a third or 2/3.
Mm-hmm.
It's even possible you'll get a 1/4 and 3/4. Generally,
Yeah,
most.
I've seen a quarter. Yeah, I mean the quarters,
there you go.
quarters and the halves are a little more straightforward. I feel like the thirds are kind of weirder.
Yeah, they're just less. You have less experience with them, right? We generally don't cut pizzas into thirds. We cut them into halves and then quarters and then eighths, right? So that's usually the issue there. But yeah, in fact, mathematically, you can go as far as you want in theory. Like there are pretty complex compounds out there. So for example, you could have, if you had 0.2 or 0.4 or 0.6 or 0.8, right? That's 1/5, 2/5, 3/5, and 4/5. And even a sixth is like 0.166 is 1/6, right? So in theory, there is no real like theoretical limit to how, well, there is a theoretical limit, but you could have in theory those kinds of problems. However, I'm just going to go through this real quick. It looks to me like the ALEKS problems are set up for relative. I don't think they go any further than thirds and 2/3. It doesn't look like they go into quarters, but they might. I'd have to actually look at all of the problems just to see. But what's really limiting how far they can go down is just most of these problems are just 2 elements, and they are inorganic elements. So they're like phosphorus and chlorine or phosphorus and oxygen. And those compounds, there's a limit, you don't have like P17O31. You don't have big numbers like that. So usually I would say 1/3 and 2/3 is probably what the limit's going to be. I doubt you'll see quarters and 3/4, but you might. So I would say, prepare mentally for this range right here. These ones, I don't think they're going to have you go that far. And the reason is when you start getting down to 0.2, well, 0.2 is not that far off from 0.25, right?
Yeah.
So this is 1/5 and this is 1/4. Once these numbers start getting close to each other, now it becomes a little more tricky to figure out which one it is. What if I said it was actually 0.22? Well, you might say that's a fifth, but 0.22 is actually pretty close to a fourth also. So for that reason, they're probably not going to go beyond a third, I would imagine.
But for that one, like if we did have aluminum and oxygen, it would be totally plausible that we would end up getting like Al3, what was it, Al3O20?
Yeah, the problem with that is that physically that's not possible because aluminum cannot bond to that many oxygens. You know, like that comes out to, you know, it's almost 7 to 1, right? Aluminum can't bond to 7 different oxygens. Physically, it can only bond to maybe 3 oxygens. So that's the reason that, you know, a half or a third tend to be the limits of what you're going to see. It's just this physically, these atoms can't do that kind of thing. We'll see later in the course that some atoms can bond up to 6 different atoms, but that's kind of the limit, right? Like, you know, chemists will do these little things where they'll try to force more atoms on one so they can get 7 in there, you know, so they'll do that kind of stuff, but you don't tend to see that in nature. 2 to 1, 3 to 1, 4 to 1, 5 to 1, not much more than that, right? So 7, that was, when I saw that this was 3 to 20, I was like, hey, wait a minute, that's not possible. You're not gonna have 3 to 20. You might have 3 to 9, you know, 1 to 3. But that's what led me into saying, take a look at this. I wrote the element wrong. It was chlorine, not oxygen. Chlorine weighs more than oxygen. So what's gonna happen is you're gonna have fewer chlorines. You're not gonna have 6.64 chlorines. You're gonna have half as much. You know, that's what it'll work out to be. So it's probably going to be 1 to 3 or something like that. So let's take a look. So it looks like all I need to do is really just get rid of this part, right? Because what's going to happen is this number right here is still going to be bigger than 0.7502 because 79.76 divided by 35 is a little more than 2. So let's see what that works out to be. 79.76 over 35.45, 2.2499. So this is the larger values still, right? The aluminum is smaller. So aluminum over aluminum is 1, chlorine over aluminum. That looks like about 3 to 1. 2.24. Oh,
Yes, about
2.2499. I wrote that number down. Okay. 2499 over 0.7502. It's 2.999, right?
Yeah.
That one we don't even have to worry about multiplying by 2 because that's essentially 3.
Yes.
So it's a 1 to 3 ratio there. We're set on that one, right? That one's a little easier. It might be a little easier because they're also going to have you figure out the molecular formula. And since you have to do that extra step, they wanted to make that a little bit easier, right? But, you know, there you go. So that means we've got the empirical formula. We don't have to multiply by 2 because they're already whole numbers, right? It's 1 to 3. So it's aluminum, 1 aluminum, and then 3 chlorines. That looks a lot cleaner, right? A lot cleaner than the oxygen one did, okay? Now we can do this last step. This number right here, which, by the way, there are different ways of figuring out molar masses of compounds, but the best way, really the best way, is what's called a mass spectrometer. They're amazing devices. What you do is you take a sample, it can be a tiny bit. They've built these things on Mars now. They have mass spectrometers on Mars on these rovers. When I started in science, they were like this big or the size of a room. Now they can make them about this big. Okay, it's really cool. So essentially what you do is you take a little bit of the sample. If it's a solid, you just zap it with a laser that creates such a high temperature, it vaporizes it, converts it into a gas. But not only does it vaporize it into a gas, it knocks off an electron. And so if it knocks off an electron, it's now a positively charged molecule, and that's an ion. Then you have these electric fields, just high voltages. If this thing is positively charged and you put a negative voltage here, it'll start accelerating toward it. And what you do is you put a little hole in here so that it goes through the hole. You put another more negative voltage here with the hole, it goes through that hole. And this thing just starts going flying down. So all these ions will fly down. And then what happens is you put a magnet at the end, and the magnet will deflect them based on how heavy they are. The heavier ones don't deflect all that much, but the lighter ones deflect a lot. And then you have a detector, a little grid like you would have on your phone, essentially. And these detectors will essentially, anything that's charged will give a little voltage out. So you essentially get a little spread of masses, so you can figure out how much they weigh. And these things are really precise. They can give you 6, 7 significant figures, and they're really very, very sensitive. You can have, 10 to the -9 moles, and it can detect these things. So that's what they use on these. One of the things they use on these rovers on Mars. So, okay, so let's find out the molecular. Here's the the molar mass. Let's find the molecular formula. So here's what you do. We know the empirical formula is AlCl3. So what I'm going to do is I'm going to ask, what would be the molar mass of that particular compound? That's easy. You just add the atomic masses. You just add the molar masses of each element. So aluminum is 26. Oops. Oh, I'm sorry. Just put this in here in a second. Aluminum is 26.98, right? We have that up here at the top. And then chlorine is 35.45. So let me put that in here. 26.98. And then chlorine is 35.45. Oops, 45. Okay, so we're going to figure out how much that weighs. $133. So that's how much, that's the molar mass of aluminum trichloride, AlCl3. So then you ask yourself, okay, if that's how much AlCl3 weighs, let's compare that to the molar mass of the compound that was given, 266.64, which is up here at the top, right? See how those two numbers are related to each other? 266 is twice 133. What that tells us is the actual compound weighs twice as much as the empirical formula. So if the empirical formula weighs 100, but the molar mass weighs 200, it's twice as heavy. If the empirical formula weighs 100 and the molar mass of the actual compound is 300, that would be 3 times as much. So formally, what you do is you take this molar mass over here, and you divide it by this molar mass, the one for the empirical formula. And what you get is 2. So that tells us the molecular formula. Remember, that's the actual compound. It weighs 2 times the empirical formula. 2 times. So if the empirical formula is AlCl3, that means the molecular formula would just have twice as many atoms. You just double the number of atoms, okay? So that would give you 2 aluminums instead of 1, and 6 chlorines instead of 3. So you're just taking these numbers here, 1 and 3, and you're multiplying them by that ratio, 2 and 6.
Professor, why aren't we doing 2 as just the coefficient and getting to AlCl3? Why are we
Because we're trying to find the formula. And the formula doesn't have a coefficient in it. A coefficient is what we use when we balance an equation. So a coefficient is telling you how many of these react with how many of those. But if I were to say, it's kind of like this. 2 bicycles are not the same as 1 car, right? like it's true, 2 bicycles have 4 wheels like a car does, but a car weighs differently than 2 bicycles. So what we're doing here is we're saying, once you get the empirical formula, all that's telling you is that there's 1 aluminum for every 3 chlorines in this compound. But it doesn't necessarily tell you how many aluminums there are and how many chlorines. It's just telling you what the smallest ratio is. To find the actual number, you use the molar mass, 266. That tells you it's got to be 2 aluminums and 6 chlorines, right? If you think about it, that 266.64, the only number of aluminums and chlorines that works for that is 2 and 6. So if I were to say 2AlCl3, okay, the molar mass, doesn't matter what this number is, that's just telling you how many you have. The actual molar mass would be 26.98 plus 3 times 35.45, right? The molar mass is 1 mole of this substance. So 1 mole of that substance weighs 133.33, okay? This would be the actual formula. So that actually tells us a little bit about it. It probably looks something like this. There's 2 aluminums in there and 6 chlorines, okay? That's fundamentally different than this. That would be this. 2 of these. Two separate objects is not the same as 1 large object. Okay. And there you go. Okay. So if you got, actually what happens sometimes when you do these problems is you might actually end up with the same number. So if they told you the molar mass was 133.3, when you do that division, you would get 1, and that would tell you the empirical formula is the same as the molecular formula. And that can happen. So for example, carbon dioxide, when you do a problem with carbon dioxide, CO2, the empirical formula is the same as the molecular formula. Okay. Let's see, let's do one more. So here's one with nitrogen and fluorine. Let's do this one. Okay. Okay. So this one, they have a compound. Again, the goal of this one is to find the molecular formula. So if you're finding the molecular formula, they got to get, there's actually a different way to do these problems where you just use the 104.01 and then figure it out backwards. I've seen some students do that, but I'm going to show you the method that textbooks use. So you have a molar mass of this compound, 104.01 grams per mole, and you've got 2 elements in it, nitrogen and fluorine. Their mass percentages are given. Write the molecular formula. Okay, so very similar type of problem. Okay, so I'm going to write this down again. Molar mass. I'm not actually going to use this till the end, right? But I'm still going to write it down here. And then we've got nitrogen. Nitrogen is 26.93%. Fluorine is 73.07%. And then their molar masses are easy. These ones I remember. 14.01 and 19.00. Okay. All right, so again, the idea would be that if we're given percentages, if those are mass percentages, then we can write them as grams. Okay, now we can convert each one to moles. So 1 mole of nitrogen is 14.01 grams. These are large masses, by the way. When people do these experiments, they wouldn't likely use 26.93 grams. they're more likely to use like 26.93 milligrams, like the thousandth as much, but they're using nice big numbers. Divided by 14.01, and you get 1.922. And the fluorine is 73, so there's more fluorine. This is going to end up being NF3 most likely. So 73.07 divided by 19. Oops. .8457, 58, I guess. Is that right? Wow, that actually looks like 2. Looks like a 2-to-1 ratio. I was going to say it's going to be 3, but it actually looks like it's 2. Okay, so yeah, I guess that's right. Okay, so again, the nitrogen is smaller, right? This one's smaller. This one's larger. Okay, so nitrogen divided by itself is 1. And then fluorine divided by nitrogen, you divide by the smaller. So 3.8458 over 1.922. That looks like 2, right?
Yes, it's 2.
Yeah, it's 2. So it's 1 to 2. Okay, so they tricked me on this one. I was wrong. So it's actually the empirical formula is NF2. Then you ask yourself, how much does NF2 weigh? What's the molar mass of NF2? Well, you got 1 nitrogen, and you got 2 fluorines. So 14.01 plus 2 times 19, and you got 52. Okay. Perfectly fine. Now, compare that number to the molar mass of the molecular formula, right? They're not equal to each other. That means the empirical formula is different from the molecular formula, right? So what you do is you take your molar, it's a molar mass ratio. So for the molecular formula, divided by the molar mass of the empirical formula. So that is 104.01 over 52.01, and that's 2. That tells you the molecular formula is twice as heavy. So that means it has twice as many atoms, right? 2 atoms weighs twice as 1 atom, right? So what you do is you just take your NF2 and you change that to N2F4. And there you go. So here's our N2F4. Actually, that makes sense, N2F4. I can draw the Lewis structure for this one. We'll get into this later, toward the end of the course. But there are these things called Lewis structures where you draw in all the dots to represent electrons in the valence shell. It's kind of cool stuff. We don't need that yet. All we need to do at this stage is say, hey, it's got to be N2F2. And you can check your answer. You just say, look, suppose I thought it was N3F7. I did this whole thing and it was N3F7. You check here and you see, does N3F7 weigh 104? If it does, that's probably the right answer. If it doesn't, though, that tells you there's some mistake in there. Okay, and that's pretty much the idea. Okay, any questions on that problem? Cool. All right. Let's see.
Professor, I have a question.
Sure, go ahead.
Are the exams on Alex or will they be on Blackboard?
Alex.
Okay.
So you can do this now. You can go on to what's called the assignments tab in Alex and look at the practice exams. So there's a practice exam for chapter 3, which will be your first exam, and you can practice that exam.
Okay.
It's timed. I gave you like 2 hours, I think, for it. but you can take it multiple times. It's longer than the actual. The actual exam has 10 questions. The practice exams have like 20, just to give you more practice, but it's all on Alex. And you can actually take the exam already. It's already up, but I think the deadline, I forget what I put the deadline is, like Sunday the 26th or something
Yeah,
like that.
I saw them. I just wanted to make sure that it wasn't just practice and the actual exam or actually on Blackboard. But
Right, exactly. Yeah, I don't have any exams on Blackboard. They're all on it.
got it. Thank you.
Cool.
Also,
Okay. The
also,
only,
Professor, for
yeah,
the,
go right ahead. Go ahead.
I'm sorry. Also for the test too, the practice exams is, each practice exam is, would essentially be on the test, right?
Yeah, not exactly. They don't match up perfectly. There's a little, I tried to match them up relatively well, so they're not 100%, but they're pretty close. The practice exam has more problems in it, so there will be problems on the practice exam that are not on the regular exam that you get graded for. But I would say at least 90% of what's on the practice of what's on the actual exam is on a practice exam. So they don't match up perfectly, but they're pretty close.
Okay.
But like I said, the practice exams are longer. Okay. So because you have more problems in them. So, you know, you'll have 2 hours to do those. But yeah, there you go. Okay. So I would recommend, in addition to doing the objective and in addition to doing the homework problems, these, topics, you can every once in a while open up a practice exam, practice exam 3 and just some practice on it, right? And you'll see that, you'll see what the actual exam is going to look like, particularly for the first one, right? Because for the first one, you don't know what to expect. So if you do the practice exam, that will help you. There you go. Okay, great. So so just to make one quick point, there's one more type of problem at the end here that they throw in, which, sorry, let me do this better. So I just want to, we don't have time to go over it, but I'm going to show you what it looks like. There you go. So the only difference here is that they give you 3 elements instead of 2. So same idea. These are grams, divide, convert them to moles, all 3 into moles, divide by the smallest of the 3. Okay. So one of them will be 1, the other ones will be different numbers. We'll have a formula with 3 elements, right? And then you add up the molar masses of each element to get the molar mass of the empirical formula, divide this by it. Same idea. It's just that you got 3 elements. Same idea though. Okay. And there you go. So tomorrow, what I'm going to do is I'm going to go over the next subject, which is, here, let me look at it here. Section 3.6, which is, here, I'll bring this up here. 3.6 is calculations with balanced chemical equations. And I hope to have time to do limiting reactants tomorrow as well. But at least 3.6, which is using chemical equations to do these calculations. So here's an example, for example, right there. So that's section 3.6. So we'll go through that tomorrow. And if I have time, I'll get into 3.7 as well. Okay, awesome. So have a great day. And see you tomorrow.
Thank you, Professor.
Thank you, Professor. Have a great day.
All righty. Bye-bye.
Professor,
Yeah, go ahead.
tomorrow is a holiday. It's Yom Kippur.